Hello students, welcome to another physics session. We on the topic photoelectric effect. Last time we were able to look at Einstein's equation on photoelectric effect, and in this session I want us to look at a few examples on calculations concerning the Einstein's equation on photoelectric effect. Just a recap of what we found on Einstein's equation. We found that the radiation energy HF, if it is sufficient enough, it will, or more than the work function, it will give us both the energy to eject the electrons from the metal surface, and the extra energy will be absorbed by these photoelectrons as kinetic energy. And that means that HF, the work function, is given also by Planck's constant, but this time times the threshold frequency. And the kinetic energy of these electrons will be given by a half the mass of the electron times the velocity squared. And we can also have it as HF, that is the energy of the radiation, is the Planck's constant multiplied by, instead of the threshold frequency, we now have the speed of the radiation divided by wavelength, the threshold wavelength. This plus a half the mass of the electron times the velocity of the electron are squared. Remember that the frequency of this radiation, for it to give us these two energies, then that frequency must be greater than the threshold frequency. Then in that case, it will give us both work function and kinetic energy. If this frequency is equal to the threshold frequency, then it will only be able to give us the work function, but you're not going to get the kinetic energy. And if this frequency is less than threshold frequency, then you're not going to get anything here because the energy will be less than the work function. Let's look at an example here. The minimum frequency of light, minimum frequency, that means that we are talking of the threshold frequency that will cause photoelectric emission from potassium surface, is 3.5 times 10 to power 14. So you can immediately pick that one out, that the threshold frequency is 5.3 times 10 to power 14 hertz. A certain radiation on the surface causes photoelectrons to be ejected with a speed of 7.9 times 10 to power 5. We have the speed of those electrons, 7.9 times 10 to power 5 meters per second. Then we need to calculate work function of potassium, maximum kinetic energy of photoelectrons, and finally we look at the frequency of the source of radiation. The quantities we've been given, the threshold frequency and the velocity. Then we go ahead, we get the work function of potassium. Work function equals to Planck's constant times the threshold frequency. Therefore, this work function will be 6.63 times 10 to power negative 34 multiplied by the threshold frequency, which is 5.3 times 10 to power 14. On multiplying 6.63 times 5.3, it will give us 35.60 times 10 to power negative 20. Which translates to, in standard form, 3.560 times 10 to power negative 19 joules. That is the work function. Its energy, therefore SI unit in joules. Part 2, we need to get the maximum kinetic energy of the photoelectrons. We already have the velocity of the photoelectrons. Then we go ahead, kinetic energy is given by a half mass of the electron times the velocity squared. which will be a half. The mass of an electron is 9.11 times 10 to the power negative 31 kilograms. Then we multiply that by the velocity, which is 7.9 times 10 to the power 5, that squared. If I separate this will be a half times 9.11 times 7.9 squared times 10 to the power negative 31 times 10 to the power 10. On simplifying that, this gives us 284.278 times 10 to the power negative 21. 2 in standard form, 2.843, leave it to 4 significant figures, multiplied by 10 to the power negative 19 joules, still kinetic energy. Part C, we want to calculate the frequency of the source of radiation. The frequency of the source of radiation. We've seen that the energy of the radiation was able to give us both the work function and the kinetic energy, which we've already calculated the work function and we've also calculated the kinetic energy. Therefore, HF will be equal to work function, which we found to be 3.56 times 10 to the power negative 19. We add the kinetic energy, which is 2.843 times 10 to the power negative 19. We already know the Planck's constant, 6.63 times 10 to the power negative 34. We multiply by the frequency of the radiation, which we want to determine, will be equal to, on adding this total energy here, 3.56, we add to 2.843, we are going to get 6.403 times 10 to the power negative 19, and therefore F, the frequency, will be 6.403 times 10 to the power negative 19 divided by the Planck's constant, 6.63 times 10 to the power negative 34, which gives us a frequency of, this will be 0.9658 times 10 to the power negative 19 times 10, bring this one to the numerator to give us 10 to the power positive 34, which will give us 9.658 times 10 to the power 14 hertz. This will be the frequency of the radiation. Just to note, this frequency is greater than the threshold frequency. That's why it has been able to give us both the work function and the kinetic energy, because F was greater than the threshold frequency. Join me in the next session as we look at another example.